Hi everyone, my name is Viraj and welcome to this class. Let's start the next chapter, which is electromagnetic waves. This chapter is like really easy chapter, kind of theoretical and some formulas are there. We will just first understand the theory and then we will see what kind of formulas are there and how to apply those formulas in different type of problems. Then we will see what are the properties of electromagnetic waves and how many types of electromagnetic waves are there. Okay, so if I start this discussion, so these waves, electromagnetic waves, these are basically proposed by J.C. Maxwell. Maxwell theoretically proposed these waves, existence of electromagnetic waves, and this discussion is happening around 1870s, 1865 to 1870. Around this period, he theoretically proposed existence of electromagnetic wave, and later around 1885, Hertz discovered the first radio waves. Clear? So this is discussion around this era. So let's see what was happening around that time. So Faraday, which we have already covered, Faraday experiment. So Faraday did one experiment, Faraday proposed the laws of electromagnetic induction. They were named after him as Faraday laws of EMI. In the previous chapters we have covered this. According to it, whenever there is change in magnetic flux, through a coil, then it induces some EMF in the coil, which is given by rate of change of magnetic flux. EMF is given by d phi by dt, where E is induced EMF and d phi by rate of change of magnetic flux. This we have already covered. So what is the takeaway? Takeaway is, according to Faraday's experiment, so if magnetic field lines are changing through a coil, if magnetic flux is changing through a coil, then it induces current in the coil, or it induces electric field around it, which produces current in the coil, which we call as induced EMF. So we can say time varying, that is the takeaway, that is time varying magnetic field, induces time varying electric field. That is the key takeaway. Electric field will generate EMF. This is given by Faraday. It says if magnetic field is changing with time, that it induces time varying electric field. Clear? Then someone asked, what will happen if we change electric field in space? Will it generate magnetic field? So Maxwell asked this question, if what happens if we try to change electric field in the space? Will it generate magnetic field also? Converse is also true or not? So that was the main question. Clear? So what will happen in this direction? Will it be true or not? That was the main question. So this we have already covered. He said, when magnetic flux passing through a conducting loop changes, then EMF is produced in the loop, and for a closed circuit, the current will flow in the loop. And for open circuit, only the induced EMF will be there. But, so change in magnetic flux produces induced EMF. But Maxwell did something opposite to it. What was it? He placed the setup like this. In this, what he did, he placed two magnetic needles, one near the wire having conduction current, that is having actual current in the wire, and there is a needle placed around it. So what will happen? A current generate magnetic field around, a current carrying wire generate magnetic field around it. So this will be what? Deflected, because of magnetic field produced by current carrying wire. So this must be deflected, and it was the case. It has been observed that this magnetic needle got deflected. But there are two capacitor plates, and within the capacitor plates there is no current as such, no electron is flowing, because positive charge got stuck here and negative charge got stuck here. So what is happening in this case? So no current is flowing through it. So if no current is flowing, then there should be no magnetic field between this region. So this needle shall not deflect at all. But what was the case? This needle also got deflected. So that was the first time. So when both the two magnetic needles are placed, one inside the capacitor and another outside the capacitor plate, that is near the current carrying wire, and Maxwell observed deflection in both the needles. So what was the conclusion? How you will explain the deflection of this magnetic needle which is placed between the capacitor plates? So this was the main question which generated this idea. What was the idea? He tries to explain it. He tries to explain it with different concept. He tries to explain this with a hypothetical current. He named it displacement current. We will be studying that also. And he explained that whenever we are charging a capacitor, so what is happening? Electric field is continuously increasing. Electric field is continuously increasing. So this electric field is increasing with time. So it is varying. It is a time varying electric field. Why it is increasing? If I ask you why? Because charge on capacitor Q is increasing with T. So Q is increasing with time. So you will say as capacitor is getting charged. So charging of capacitor is what? So you will write Q naught 1 minus e power minus t by tau. So this we have already covered in capacitor classes. So as the time increases, this Q increases. So charge increases, it increases the electric field around it. So T increases the Q and Q increases the electric field. So what will happen? The same case which we just took. So he says that whenever there is a time varying electric field, it must produce a time varying magnetic field. So this was the conclusion, and this conclusion was proposed by Maxwell, that if you change electric field or electric flux with time, then it produces magnetic field, and if you change magnetic flux with time, then it produces electric field. Clear? So they both are interlinked. So Faraday tries to combine not just magnetism depends upon current, but reverse is also true. Electric field, changing electric field can produce magnetic field, and changing magnetic field can produce electric field. So both are interconnected domain. That was the first theoretical explanation that was provided here. Clear? So what is happening? He said there is a discrepancy in Ampere's law. With this explanation, he proposed one more theory. He said there is some discrepancy in Ampere's law. What is Ampere's law? That line integral of magnetic field is equal to line integral B dot dl over a closed loop is always equal to mu naught times the enclosed current. So he says if you took 2 Amperian loop, one here and one here. So what he says, that integral B dot dl at point x is this point. At x is this point, if you take this Amperian loop, so there is actually some current flowing through it. So this Amperian current is integral of B dot dl must be equal to mu naught times I. This is the enclosed current. So this is valid for x. But for y, integral of B dot dl is equal to mu naught times 0. Mu naught times 0. It should be the case as per the Ampere's law. This simply means B at y must be 0. Magnetic field at point y must be 0. But this magnetic field is getting deflected, which is not true. Can you say which is not true? By is not 0 because this needle is showing some deflection. So he says that there is something wrong with this formula. This formula is correct here, but it is not applicable in this case. So either it is conditionally applicable or either something is missing here. Something is really missing in this case, which is not being captured, which is not getting captured in Ampere's law as it is. Clear? So he explained one more theory. He gave that there is magnetic field due to changing electric field or changing electric flux, or changing electric flux can produce a hypothetical current. He named it hypothetical current. Whenever there is electric flux change in the space, then we can assume there is a hypothetical current in that space, which we call as displacement current. So he modified this law, he modified this equation, and he corrected this equation and gave Maxwell Ampere's law and the definition of what? So there is a discrepancy in Ampere's law and modified Ampere's law is needed. Modification in Ampere's law is needed, he proposed, because this statement was not true. Then he gave a concept of displacement current. What he suggested? A current which is developed due to the changing electric field. That is saying due to the changing electric field. Current which is developed by, the cause is not flow of electron. This current is not due to flow of electron but due to changing electric field or changing electric flux is called displacement current. That simply means whenever there is electric flux changing in the space, then we will be assuming there is a hypothetical current in the space which is not caused by motion of electron. Clear? So what is the value of this? So he explained that displacement current is nothing but epsilon naught times rate of change of electric flux, not magnetic flux, electric flux. And what is electric flux? Electric flux is electric field into area. The rate of change of electric flux into mu naught. This is the definition, or theoretically he derived this formula for what? Displacement current. Clear? And what is conduction current? Conduction current is the current in the wire. This is the conduction current in the wire. So this part is conduction current and this part is displacement current. So displacement current is given by this. Conduction current is nothing but rate of flow of charge, that is dq by dt. dt. So this is the conduction current, this is the displacement current. Both are having a unit of ampere only, but the basic cause is it is due to flow of electron and it is due to changing electric flux in the space. Clear? So that is the meaning. And one more thing we will be deriving, that magnitude wise total conduction current in wire, to maintain the continuity of current, the current in this space, theoretical current in this space, magnitude wise the total conduction current in wire would be total displacement current between the capacitor plates. That is the relation that we will be deriving. So not only the current produces magnetic field, which is the case here, current produces magnetic field, but changing electric field also produces magnetic field. That was the conclusion drawn by what? Maxwell's theory. This was the biggest achievement. We are able to talk over phone, you are able to see this stream, you are able to watch videos over internet or maybe some platform. So that's all because of electromagnetic waves. You can listen to radios, you can use ovens, you can use ultraviolet light, you can use X-ray machines. These are the outcomes of Maxwell theory. He proposed that there exists some electromagnetic wave, that is electric field, changing electric field produces changing magnetic field and changing magnetic field produces changing electric field, and this fluctuation travels in space, which we call as electromagnetic waves. Clear? And then there are other properties associated with these waves that we will be studying, but this was the initial thinking that got developed in the mind of Maxwell, which proposed this theory. Clear? So what is the discrepancy? How he resolved the discrepancy? He said that the displacement current in the wire would be something like this. Just now I wrote ID equal to d phi E by dt. So it can be written something like this. You can put the value of phi E as electric field into area, you can put, and this electric field you can also put sigma by epsilon naught, and sigma is QE. So he is just proving that area got cancelled, epsilon naught got cancelled, so it is nothing but dq by dt only, and dq by dt is what? Conduction current. So theoretically they are equal. Theoretically conduction current and displacement current, total value of this and total value of this are equal in magnitude. That simply means if current at any instant of time in the wire is 10 ampere, then displacement current total would be 10 ampere only. Clear? So that is the case. Shall we move? Yes. So that is the case, they are proving it. Then what modification he did in Ampere's circuital law in this case? Because there was magnetic needle, so he proposed for x we can simply write integral of b dot dl equal to mu naught. He said take both the currents, you also write conduction current plus you also write displacement current. At x what is happening? Only conduction current is available, no displacement current, so ID would be 0. So the value would be nothing but mu naught into IC. At y what will happen? Integral b dot dl would be there, so mu naught times conduction current plus displacement current. He said you need to take both the effect, displacement current effect plus conduction current effect. So at y what is happening? There is no flow of electron at this point, so conduction current would be 0 in this case. So he said for y loop integral of b dot dl would be mu naught times ID. So what is in general? He said there is magnetic field because of displacement current and there is magnetic field at x because of conduction current. Now in general, he derived this formula. He write a modified formula for Amperian loops. Integral of B dot dl is equal to mu naught times conduction current plus displacement current. And we know what is the value of displacement current. Displacement current is given by epsilon naught d phi e by dt. Clear? So this becomes the modified Amperian Maxwell law. Ampere's Maxwell law. Clear? So this is Ampere's Maxwell law, and here this is Maxwell correction which is done by Maxwell, and this is displacement current magnitude. Yeah. So if you write this is the Maxwell Ampere's law which is corrected after finding the discrepancy. Clear? So what are the properties of displacement current? One thing, we know the magnitude. Magnitude is given by, there are two properties. Magnitude is nothing but epsilon naught d phi e by dt. If I put, we can also write area, we can take common, or we can write dE by dt. For phi e you can put E into area. So this value can be taken up or this value can be taken up, that is up to you. These are the mathematical properties, that mathematical formula you can use. And one more thing, that total value of displacement current is nothing but total value of conduction current in wire, that is also true. Apart from this, one thing, displacement current is not a conventional current because it is not because of flow of electron. It is not, it only exists when there is changing electric flux in the region. Whenever electric field change in a space, then displacement current will exist. Displacement current does not exist under steady state conditions. It does not exist under steady state conditions. That you need to take care, because in steady state what will happen? Capacitor will become fully charged, electric field will not further vary anymore, so electric flux will not change with time, so displacement current will disappear. Clear? And the conduction current and displacement current together satisfy the property of continuity. Continuity means if current in the wire stops at positive plate of the capacitor, then to maintain the continuity, there is a hypothetical current which we call as displacement current and of same magnitude flow through the space. That maintains the continuity. Clear? So this was the concept of displacement current. We will see question on this also. Let's see the question. Read this question. There is a parallel plate capacitor of area 16 centimeter square and separation between the plates is 10 centimeter. Now it is saying it is charged by a DC current. It is being charged using a DC current. Consider a hypothetical plane surface of area 3.2 centimeter square inside the capacitor and parallel to the plates. Okay, let's draw one diagram. Suppose there is a capacitor. It is being charged using some DC battery, and we have also closed the key for this. We have also closed the key. We know this plate area is what? This plate area is 16 centimeter square. The unit is 16 centimeter square. And it is saying there is a hypothetical, there is one hypothetical area between the plates of this capacitor. Hypothetical area, its area is 3.2 centimeter square. This is the question. At an instant, at some instant, what is happening? The current through the circuit is 6 ampere. It is saying at some time t, the current in this circuit, that means conduction current, is what? 6 ampere. Then it is asking at the same instant the displacement current through A naught. This area was A naught. Then what is the value of displacement current through this hypothetical surface? What it would be? We need to check for the value. See, there would be changing electric flux in this region or changing electric field in this whole region of 16 centimeter square. So what is happening? The total displacement current would be equal to total conduction current. So displacement current total, what it would be? 6 ampere only. Total displacement current through the whole space would be 6 ampere. Now I need to find current through this space only, that is 3.2 centimeter square. So can I use unitary method that simply says if area is 16 centimeter square, if my area is 16 centimeter square, then my current would be 6 ampere displacement. That means through the whole area between the plates of capacitor, the current would be 6 ampere. If we consider the area as, what is the current flowing through 1 centimeter unit area? So you will say that 6 by 16 ampere. Unitary method. 16 centimeter square has a current of 6 ampere. 1 centimeter square will have a current of 6 by 16 ampere. Then what is the current flowing through 3.2 centimeter square? So you will write, sir, 6 by 16, that is current flowing through unit area, into 3.2, this much ampere. So you just calculate this value. So this is my displacement current required. This is my displacement current required. What is this value? If you calculate, it would be 1.2 ampere. That would be your answer. Clear? But they are asking in milliampere. So this value can be converted in milliampere. So you will write displacement current required would be 1200 milliampere. Clear? So such a question can be built. This is very interesting question. If you read it once, and sometime this will happen that you won't be able to understand the approach. You won't be able to pick the pen that where to start this question. Clear? So now you would find it easy, that is it just a unitary method. But first you should have this understanding that whatever the current flowing through the wire, to maintain the continuity, the total displacement current should be same. Then for 16 centimeter square it would be this, for 1 centimeter square it would be this, and for any given area you will multiply 6 by 16 into the area required. Okay. So through this area, this would be what? 1.2 ampere or 1200 milliampere. So answer would be 1200. Clear? So that is how they will pose you question from this, or they can pose you question based on the definition, just like I explained you here. Yes, these are the direct definition. This one is easy. If they give you question on this, so that they will give you a very easy question, so you can just directly differentiate. That is not a case. But yes, if they want you to analyze the question, then think about the question, and they want to check your deep understanding, then they will give you a question like this. Clear? So let's move to next topic. Then Maxwell proposed Maxwell equations. What are Maxwell equations basically? These are 4 set of equations which are basically 4 fundamental laws of electricity, magnetism, or electrostats or magnetism. He clubbed together all those 4 fundamental laws, and these set of equations are known as Maxwell equations. Maxwell, in the process of unification of electricity and magnetism. So what he was trying to achieve? He was combining 2 domains. One was electricity and magnetism. Faraday said magnetism is linked to electricity. He also said electric field is also linked to magnetism. So he was trying to combine these domains. But in this process, actually he combines the three domain, optics also. Because in later part, we got to know that light is also an electromagnetic wave. So while combining these, he attached all these three fields together. So this was the outcome that was achieved by Maxwell, that unification of these three great domain of physics. Clear? So he brought together four already existing equations and modified them. One of them he modified, Ampere's equation, and he further stated that these four equations completely define the electromagnetism. Solving these equations will give you the equations for electromagnetic wave. Combinedly, if you solve them, then you will get this. And what are those four equations? These are Gauss law in electrostatic, Gauss law that we have studied in electrostats, Gauss law in magnetism, we have studied integral of B dot dA, here integral of E dot dA, Faraday law, integral of E dot dl, and Ampere's Maxwell law. Maxwell because it is modified also. So Ampere's Maxwell law, just we have studied the discrepancy of Ampere's law. So Ampere Maxwell law is integral of B dot dl. So we will write those equations, but these were the four fundamental laws of electrostatics and magnetism. He combined them, and these equations combinedly known as Maxwell equations. Clear? So what are Maxwell equations? We will try to write. First, he will give you the equation for what? Electrostats. Gauss law in electrostat. What is Gauss law in electrostat? Integral of E dot dA, or sometime we write E dot ds. dA is stand for area. Over a closed loop is nothing but Q enclosed upon epsilon naught. That is the meaning. Q enclosed by epsilon naught. What is Gauss law in magnetism? Gauss law in magnetism says integral of B dot dA is always 0. This is the second Maxwell equation. Then third Maxwell equation is what? Faraday's law of EMI. Faraday law says integral of electric field E dot dl, which is induced EMF, nothing but induced EMF over a closed loop. E dot dl is nothing but minus d phi b by dt. That is the takeaway. And fourth one is Ampere's Maxwell law. He also said integral of B dot dl over a closed loop is mu naught times conduction current plus displacement current, and displacement current is given by d phi e by dt. So this is the formula. So this is the four set of equation which is combinedly known as Maxwell equations. Gauss law in electrostatics, Gauss law in magnetism, E dot dA, B dot dA, E dot dl, B dot dl. So you need to know these values because such a questions have been asked previously in your exam and in other competitive exams also. Clear? If you see, this was the question that got asked in PYQ. So if you list 1, list 2 and try to combine, what is Gauss law in magnetostatic, Gauss law in electrostat, E dot dA. Which is E dot dA? E dot dA, this one. E dot dA is, this one is nothing but charge enclosed. Rho is charge density, rho into dB, dq. dq ka integral is what? Total charge by q epsilon naught. So this matches with this. Then Faraday law, integral E dot dl, this one. Magnetostatic, B dot dA. Ampere circuital law, this one. Ampere's law is this one. And if it say Ampere's Maxwell law, then this I becomes conduction current plus displacement current. So both the values must be added. So this is how you try to plan out this. Clear? So yes, one more thing, they can write something like this to just represent the charge. they can write something like this, integral B dot dA. What is B dot dA? Flux, d flux na, total flux. So phi b can be written something like this. So they will try to give you some milder term also or some tougher term also for this. So please remember all these equations for your final exam also, and just try to memorize this accordingly. Fine, this is very easy question and it can be solved easily. Then someone asked, what is the cause of electromagnetic wave? See, whenever charged particle moves, so if the charged particle is at rest, that means its velocity is 0. So it only produces what? Electric field. That is, a charged particle at rest can only produce electric field. Clear? Charged particle at rest only produces electric field. Then if charged particle is in uniform motion, that means it is having a constant velocity, then it produces in its surrounding both electric and magnetic field. So both electric and magnetic field is produced by a moving charge which is moving with uniform velocity or constant velocity. That is, no acceleration is there. So rest, then electric field. If uniform motion, then both electric field plus magnetic field will be produced in its surrounding by a moving charge. But the third case is, what if the charge is accelerated? That is, it is accelerating, like if it is oscillating, if it is oscillating charge, if it is oscillating like this, it is coming back, then it is going in this direction, then it is coming back. So it is a oscillating charge. So velocity direction is changing. Then what is happening? Acceleration would be there. So accelerated motion of a charged particle. So this is the source of electromagnetic wave production. Whenever a charged particle gets accelerated, then it will produce electric field, time varying electric field, which will produce a time varying magnetic field around it. And both fluctuations, what? They are fluctuated everywhere in space. So this disturbance propagates in space, and this disturbance which is propagating in space is known as electromagnetic wave. They are produced by accelerated charge. So accelerated motion of a charged particle produces time varying electric field and magnetic field. Clear? Which we call as an accelerated charged particle produces electric field and magnetic field which regenerate each other, because time varying electric field produces time varying magnetic field and time varying magnetic field produces time varying electric field. So they keep on regenerating each other. They regenerate each other and electromagnetic energy starts propagating through the space, which we call as electromagnetic wave. So how to produce an electromagnetic wave? How to produce an electromagnetic wave? The simple answer is just accelerate a charged particle. If you accelerate a charged particle suddenly, then what will happen? In its surrounding, suddenly what will happen? Electric field will fluctuate, and if it got fluctuate, so it will produce a magnetic field around it. So both the fluctuations, electric field fluctuations and magnetic field fluctuations, happens in all the space around it. So, and those fluctuations propagate because they will regenerate each other. If something is varying, it is also varying the other part because they are both interlinked. So that's how electromagnetic wave propagates in space. We will see this through some analogy also, so that you can clearly develop this notion in mind. The energy associated with propagating wave comes at the expense of energy of the source which moves the particle. From where this energy is come, like what part of energy is going in electromagnetic wave? That energy is coming from the source which is the cause of this. If I am the cause, if I am trying to move it mechanically, so I am doing some work on this, so that work is going into electromagnetic energy. So it's not like energy is created out of nowhere. So energy can neither be created nor it can be destroyed, but it can be converted from one form to another. So whatever energy is given to move this or accelerate this source charge, the same work done goes to electromagnetic wave, or maybe part of that work done goes to electromagnetic wave and part of the work done goes to kinetic energy of this. Clear? So this is to follow the energy conservation. This last line is stating that energy conservation is still valid in the propagation of electromagnetic waves. Clear? Let's understand through one analogy. Suppose this is an accelerated particle which is oscillating. We call it, suppose, an oscillating charge. Now let's see LC circuit analogy. Now what you do, you have a fully charged circuit and at time t equal to 0 you closed it and there is an inductor here. So what will happen? This charge will continue to move from here to here. So electric field, this charge will try to move from here to here and neutralize this negative charge. So what will happen? I in this is increasing and so charge on this is decreasing. And electric field depends upon what? Sigma by epsilon naught. Sigma is what? Q by A epsilon naught. So it depends upon Q. If Q is decreasing, then electric field must be decreasing. So there would be a change in electric field. If this happens, then there is a change in electric field. And if current is increasing in this, so magnetic field will be changing here. So if we just look at this part only, not at this part but just at this part, so what will happen? Electric field which was initially strong, so it will slowly decrease. Okay, let's see the complete analogy. What it is saying, that it has some electric field. If it changes, if this electric field is decreasing, then it will produce a magnetic field in its surrounding. Magnetic field is generated by changing electric field, because charge is decreasing, then E is decreasing, and decrease means change, and if electric field is decreasing or changing, then it will produce a magnetic field as per Maxwell theory. And magnetic and electric field are perpendicular to each other. This we can see. Magnetic field is in this direction because it is circular, and electric field is in this direction. They are perpendicular to each other. They are making a 90-degree angle with each other. So what will happen? Now let's see. So if we try to analyze, initially the current was 0 because this was fully charged. So electric field was maximum, magnetic field was maximum. Now if it just decreasing, so current is growing but charge Q is decreasing. So if Q is decreasing, then electric field starts to decrease. And electric field in this space, electric field initially was strong, so 4 lines, now only 2 lines. So electric field is decreasing, so it will also decrease the magnitude of, but in perpendicular direction. So magnetic field will also become weak. Then after some time, when the whole positive charge goes to this side, so what will happen? It will become neutral. Electric field is 0. So what will happen? Electric field becomes 0. So at the same time, magnetic field becomes 0. Now, but current in the inductor is maximum at this. Current is growing, so it becomes maximum. Charge becomes 0. Electric field is 0. So there is a fluctuation. Electric field is reducing between the plates of capacitor, so magnetic field is also reducing. So it follows something, a path like this, but they are perpendicular. Clear? Now if you see, again there would be a positive charge because current is increasing, so now current will decrease, so this will get positively charged, this will get negatively charged. So electric field increases in opposite direction. So magnetic field also increases in opposite direction. Now it keeps on increasing, so magnetic field. So what will happen? Electric field becomes negative, so magnetic field also become negative. And if it tries to follow the same, if current grows again, then it will become maximum here, then it will again decrease, it will again become 0, then same thing happens. So what will happen? It will follow a path like this, and this will follow a path like this. But this fluctuation will keep on, and what will happen? This fluctuation of current, this fluctuation of charge in the LC circuit will keep on happening, and this fluctuation of electric field and magnetic field between the capacitor plate region, this will also happen. So they generate, the fluctuating or oscillating charge generates electric field in the space. This electric field and fluctuating magnetic field travels, and they distribute energy, they redistribute energy in some other form. This we sometime we know this is a photon. Clear? This energy goes in the form of photon. It is the same energy which we call as electromagnetic wave. Clear?